Hello everyone, my name is Dyllan Usher, and today I'll be presenting my Metis Data Science Bootcamp final project on the unsupervised analysis of climate zones with a focus in West Africa. So I came from an undergraduate math background straight into the Metis Data Science Bootcamp to start tackling real-world problems that have a positive impact on the planet. Here's some of my contact information, which will also be in the description below. The inspiration for my project came from Bobbin Gona Farmer, a smallholder farming service in Nigeria supported by the Peace Corps. They've reached out to over 65,000 people in the past 8 years, doubling the farmers' productivity and nearly tripling the profitability. By 2025, Bobbin Gona wants to reach out to over 1 million farmers, but with limited resources. How should they focus their efforts? Today, we'll look at one of many factors to consider. Which areas are most impacted by climate change? First, I want to create a map of climate zones using unsupervised clustering. Then I'll analyze the cluster movement in Nigeria. Finally, I'll develop a plan of action based on each case of unique climate change to determine which areas to focus on and in what order of priority. I obtained my data from the ERA5 monthly average dataset, a reanalysis of global climate and weather forecasts sponsored by the Copernicus Climate Change Service. Today we'll use 2-meter temperature and total precipitation to analyze the climate at a 0.5 degree spatial resolution. In order to analyze the climate, I'll first engineer some Koppen climate system inspired parameters. Then I'll cluster on global data and compare to the Koppen system as a proof of concept. Then, after performing some exploratory data analysis, I'll cluster on the West Africa region. Then I'll look at how those clusters moved by looking at the percentage change. More details on this later. Finally, I'll develop a plan of action on how to allocate Bobbin Gona's resources. This plan sounds nice, but you might be wondering, what exactly is the Koppen climate system? Well, the Koppen system is a set of rules on min, max, and mean values of annual summer and winter temperature and precipitation. It is the de facto standard for mapping climate zones. However, zone membership through the Koppen system is established through arbitrary rules. Even though they're backed by ecological research, there's still a risk of bias. Instead, I propose to use the Koppen-inspired features with unsupervised clustering on the ERA5 dataset. The features I'll cluster on will be the same parameters that assign climate zone membership in the Koppen system. The only difference is that I'll let the data speak for itself. I did have to feature engineer with caution, as our planet experiences both winter and summer because the planet is on a tilted axis with respect to the sun. After clustering with 5 clusters corresponding to the 5 major regions, the clustering on the right already looks like the Koppen system on the left. However, the clustering appears to capture more of the subtleties in the polar regions. Thus, the regions near the equator aren't as detailed. If I increase the number of clusters to the number of regions defined by the Koppen system, we start to see a more legitimate climate zone map. This is a proof of concept that shows that we can cluster on climate variables to get meaningful climate boundaries. But we don't care about the entire globe right now. We're focused on the major agricultural regions inside of Nigeria. Nasarawa State is one of them, being the largest rice producer, followed by Benue State, the largest yam and cassava producer, and lastly, Kaduna State, the largest corn producer. I'll pay special attention to these regions as they have the most at stake when it comes to climate change. However, Nigeria as a whole is largely dependent on agriculture, so other states are also very important to consider. If I look at the max summer temperature at the center point of each of these states, the results are inconclusive, but a slight temperature increase might be observed in the last decade. However, if I look at the max total precipitation, there's a slight decrease in the past decade for all 3 states. However, climate is a regional phenomenon, and looking at single values over time doesn't effectively describe the climate. Thus, clustering helps account for more general climatic trends. I clustered on the past 4 decades, training on all the data at once to retain cluster meaning from decade to decade. By clustering on both space and time, we can observe how these climate clusters have changed over time. On the left, you see the climate zones for the 1980s, and on the right, the 2010s climate zones. These zones have certainly changed. If we simply count the number of points in each cluster for each year, we can get a graph that shows the relative size of each cluster by decade. This shows certain cluster movement indicative of climate change, but we still don't know what each cluster means. We can extract meaning from the clusters by first taking the average of each engineered feature for each cluster, and then we can keep track of the cluster history for each point. Finally, we can look at the percentage change of the features that impact agriculture. For this demonstration, I chose to look at max summer temperature and total precipitation. Looking at the max summer temperature percentage change from the 2000s to 2010s, we see definite signs of extreme heat events in both the northern and southern areas of Nigeria. By zooming in, we can map out specific regions of climate change. Region 1 indicates areas with a high level of extreme heat events, marked by a 10 to 25% increase in max temperature. Region 2 indicates a medium level of extreme heat events, marked by a 15% increase in max temperature. Finally, Region 3 indicates a low level of extreme heat, marked by a 10% increase in max temperature. Now, if we look at max summer precipitation percentage change from the 2000s to the 2010s, we can see a decrease in maximal rainfall by about 30% in the northern regions of Nigeria and a decrease of about 10% in the southern regions. If we zoom in again on Nigeria, we can see that regions 1 and 2 have severe decreases in maximal precipitation, indicative of risk of drought. Furthermore, Region 3 shows a more mild risk of drought along the southern band. Now, with these regions of unique climate change in mind, I recommend first focusing on Region 1, marked with signs of drought, and a 15% increase in maximum temperature. This region is also home to the largest population densities in Nigeria, making food scarcity a top issue. Furthermore, the headquarters of Babangona farmers is located along the southwestern coast in Lagos, making this region the first logical step towards helping smallholder farmers. Also, since Benue State is the largest yam and cassava producer, I would start there, which is partially nested inside of Region 1. The regions labeled 2 mark a 30% decrease in max precipitation and a 10% increase in max temperature. Thus, this area has a severe risk of drought and a high possibility of decreased agricultural yields due to extreme changing climate. However, they aren't as populous, making them priority number 2. The third region marks a 25% increase in max temperature and is the second most populated region of the regions highlighted, making food scarcity from sun scorching a real threat, especially to non-root vegetables, which are more sensitive to heat. However, as of recent, this area hasn't seen a significant decrease in precipitation, making it the lowest priority region as of yet. But with the changing climate, we might still find this area to be drought-prone in the future. So this plan sounds nice, but before jumping to any conclusions, we have to make sure we understand the limitations of this priority ranking. For one, there are many other factors to consider when allocating resources, such as the logistical feasibility to reach some areas, along with which areas are actual agricultural centers. Furthermore, my choice of clustering algorithm and the number of clusters I used was only informed by the elbow method. In the future, I would like to compare many different clustering algorithms and look at the Bayesian information criterion to make a more informed choice on the number of clusters and which clustering algorithm to use. I'll also be keeping my eyes peeled for usable implementations of an upcoming field of data science called topological data analysis, which features more informed ways to cluster over space and time. And with that, thank you so much for your time, and I hope you enjoyed the presentation. I would also like to thank Metis Data Science Bootcamp for giving me the foundation I needed to continue my data science journey. If you have any questions, feel free to either email me or leave a comment below. Take care.